बिस्मिल्लाहिर्रहमानिर्रहीम। इकरा बिस्मि रब्बिकल लज़ी खलक, खलकल इंसाना मिन अलक, इकरा व रब्बुकल अकरम, अल्लज़ी अल्लमा बिल कलम, अल्लमल इंसाना मा लम यालम. Read in the name of your Lord, who has created all that exists, has created man from a clot. Read, and your Lord is the most generous, who has taught the writing by the pen, has taught man that which he knew not. Assalamu alaikum. Today we will cover life cycle of star and fate of universe. Low mass star, that is 0.5 solar masses, they burn up slowly and have long life of about 10 to 50 billion years. They burn red, orange and yellow. Medium mass star that have mass of 0.5 to 3 solar masses have a lifespan of 5 to 12 billion years. Our sun is a medium-sized star and has a lifespan of 10 to 12 billion years. High mass star with mass greater than 3 solar masses have a lifespan of 10 million years only. Sirius, the brightest star in the sky, is a blue star. The more massive the star, the shorter the lifespan. The reason is that the hydrogen supply of massive star is used up much quicker due to a higher core temperature of such stars. Giant gas cloud nebula. A nebula is a giant cloud of dust and gas. Some nebula come from the gas and dust thrown out by the explosion of dying stars such as supernova. Other nebula are regions where new stars are beginning to form. Stars are formed by gravitational collapse of giant clouds of gas and dust. The giant cloud of gas and dust collects together and contracts due to gravity. As it contracts, it heats up and starts emitting light. Protostar, as the gravity causes gas and dust to clump together, as these clumps gain more and more mass, their gravitational pull increases, forcing more atoms together. As it collapses, the pressure from gravity causes material at the center to heat up, creating a protostar. A protostar looks like a star, but its core is not yet hot enough for fusion to take place. The luminosity comes exclusively from the heating of protostar as it contracts. Since protostars are surrounded by dust, they are not easily detectable. A protostar becomes a star when the core temperature exceeds 10 million Kelvin. This is the temperature needed for hydrogen fusion to take place. The length of the time it takes depends on the mass of the star. The more massive the star, the faster the process. A protostar is not considered a star until it gets energy from nuclear fusion instead of gravitational attraction. If the protostar has a mass of 0.08 solar mass, it will go on to begin hydrogen burning and will join the main sequence of stars. If the temperature is not hot enough to begin hydrogen burning, it will become a brown dwarf star. A star maintains its stability through a fine balance between its own gravity, which holds it together, and the outward pressure from ongoing nuclear reaction taking place in the core. Hydrogen is star's first fuel. Sun was born with enough hydrogen to last 10 billion years. It is now 4.5 billion years old. The reaction in the core is hydrogen plus hydrogen gives deuterium plus neutrino. Deuterium plus hydrogen gives helium-3 plus gamma radiation. Helium-3 plus helium-3 gives helium-4 plus hydrogen plus hydrogen. Eventually, hydrogen in the core is used up. Temperatures are not hot enough for fusion of helium. Again, gravity takes over and core begins to contract. Hydrogen nuclei just outside the core become hot enough for hydrogen fusion to begin. As surrounding shell reignite, it creates a rapid floating star called red giant. The expansion of outer layer causes temperature to decrease. As it cools, star appears redder. Inside the core, two helium nucleus fuse to form unstable beryllium. If beryllium fused with another helium, stable carbon is formed along with gamma rays. Therefore, helium plus helium gives beryllium 8. Beryllium 8 plus helium gives carbon 12 plus gamma radiation. When the temperature of inner core reaches 600 million Kelvin, carbon fusion will begin to produce neon and helium. As carbon fusion dies off, the inner core becomes oxygen and neon. This leads to compression due to gravity and temperature increase. Fresh carbon produced in upper layer is pushed deeper, and non-burning inner core becomes surrounded by burning carbon. The reaction taking place in the inner core is carbon 12 plus carbon 12 give magnesium 24. Carbon 12 plus helium 4 give oxygen 16 plus gamma radiation. Oxygen 16 plus helium 4 gives neon 20 plus gamma radiation. Carbon 12 plus carbon 12 give neon 20 plus helium 4. When the temperature reaches 1200 million Kelvin, neon fusion begins to produce magnesium and oxygen. When neon fusion dies off, the inner core is mostly oxygen. Temperatures are not high enough for fusion of oxygen. Therefore, gravity causes compression. Compression causes higher temperature. Fresh neon produced in outer layer is pushed deeper. The reaction taking place in the inner core is carbon 12 plus carbon 12 give magnesium 24 plus gamma radiation. Oxygen 16 plus oxygen 16 give magnesium 24 plus helium 4 plus helium 4. Neon 20 plus neon 20 give magnesium 24 plus oxygen 16. When the temperature reaches 1500 million Kelvin, oxygen fusion begins in the inner core producing silicon and helium. When oxygen fusion dies off, the inner core is mostly silicon. Temperatures are not high enough for silicon fusion. Thus, gravity takes over, causing compression. Compression increases temperature. Fresh oxygen produced in the outer layer of the core is pushed deeper, and the non burning inner core is mostly surrounded by oxygen. The reaction in the inner core is oxygen 16 plus oxygen 16 gives silicon 28 plus helium 4. This is the last effort by the star to balance itself. The fusion reaction produces outward force and gravity produces inward force. When the temperature in the inner core are not enough to cause fusion of heavier elements, gravity takes over. Gravity causes compression. Compression increases temperature to enable fusion to take place in outer shell. Eventually, temperatures are high enough for fusion to take place in the inner core. At 2700 million Kelvin, silicon fusion begin to produce nickel. Silicon 28 plus silicon 28 give nickel 56 plus gamma radiation. Nickel rapidly decays to iron. Since iron is the most stable element, we are stuck. This marks the death of the star. The reaction taking place inside the core is that nickel 56 decays to cobalt 56 plus positron plus electron neutrino plus gamma radiation. Cobalt 56 then decays to iron 56 plus positron plus electron neutrino plus gamma radiation. When a massive star has completed its life, the chemical composition of the star would be something like this. When a massive star dies, its inner core is made up of iron. Iron core is surrounded by a layer of nickel. Nickel is surrounded by silicon. Silicon is surrounded by magnesium. Magnesium is surrounded by carbon, oxygen, and neon. Carbon, oxygen, and neon are surrounded by beryllium. And the outer layer is of hydrogen and helium. Eventually, if the star age, they evolve from main sequence to become red giant or red supergiant. The core of red giant is contracting, but the outer layer is expanding due to fusion taking place in the outer shell. The star gets larger, redder, and more luminous. In approximately 5 billion years, Sun will become a red giant and will consume Mercury, Venus, and Earth. In few million years, ocean will evaporate and life as we know it would cease to exist. Thus, when Sun will become red giant and engulf the Earth will be long dead. When a red giant star dies, the heat and pressure from its core ejects outer layer of the star in space. These outer layers become known as planetary nebula. Because of intense chemical reaction taking place in star, planetary nebula tends to be made of more than hydrogen. The name is very misleading. The planetary nebula has nothing to do with planets. If a red giant has insufficient mass to generate core temperatures required to fuse carbon, an inert mass of carbon and oxygen build up at the center. After such a star sheds its outer layer and forms planetary nebula, it will leave behind a core which is the remnant white dwarf. A typical white dwarf is about as massive as the Sun, yet is slightly bigger than the Earth. This makes white dwarfs densest form of matter, surpassed only by neutron star and black holes. White dwarf can range in color from blue-white to yellow, depending on how hot they are. White dwarfs are less luminous and hotter than main sequence stars. They are extremely hot and dense, although they no longer produce nuclear reactions. The characteristic of white dwarfs are high temperature 100,000 Kelvin, high mass, small size, composed mainly of carbon and oxygen, thin layer of hydrogen atmosphere, no longer produce chemical reactions, low luminosity, high magnetic field. A black dwarf is a white dwarf that has cooled down to the temperature of cosmic microwave background and so is invisible. Black dwarfs are hypothetical. The difference between the massive star and the average star is the length of their life and how they end up. Massive stars have short lives and end up as either neutron star or black hole. In massive star, a complete series of nuclear reactions lead to the production of iron in the core. The star no longer has any way to support its own mass and the iron core collapses. The outer layer of star initially begin to collapse along with the core but rebound with enormous amount of energy and are thrown violently outwards. Supernova release an almost unimaginable amount of energy. A supernova can light the sky for weeks. The temperature of supernova can reach 100 billion Kelvin. The high temperature can lead to the production of new elements which may appear in the new nebula. The death of massive star can trigger the birth of other stars. The dust and debris left behind after supernova blend with interstellar dust, producing new generation of stars and planets. If the collapsing stellar core at the center of supernova contains between 1.4 to 3 solar masses, the collapse continues until proton and electron combine to form neutron, producing a neutron star. Neutron stars are incredibly dense, similar to the density of atomic nucleus. Neutron stars also have powerful magnetic fields and are generally rotating very rapidly. The electric field that is generated by the rotating magnetic neutron star rips away charged particles from the surface of the neutron star, accelerates the particles along the magnetic field lines, and produces two beams of electromagnetic radiation. Since the beam of radiation are not aligned with the rotation axis, they sweep around in a cone. If one of the beams sweeps across the Earth, we see flash of radiation from the neutron star. Neutron stars whose beam of radiation sweep the Earth are known as pulsars. A pulsar is a highly magnetized rotating neutron star that emits beam of electromagnetic radiation out of its magnetic poles. Emission of pulsar include visible light, radio waves, X-rays and gamma rays. Electromagnetic radiation in form of beams sweep through space at regular interval. It is called pulsar because when these beams are pointed toward the Earth and flash across the Earth as neutron star rotates, we see pulses. Black holes form when the center of massive star collapses on itself. This collapse also causes supernova or an exploding star that blasts parts of star in space. Black holes have two parts. There is a event horizon, which you can think of as a surface, though it is simply a point where gravity is too strong for anything to escape. And then at the center is singularity. Nothing is darker than a black hole. A black hole is an area of such immense gravity that nothing, not even light, can escape. Black holes are really cold. They have temperature of about 0 Kelvin, but black holes' event horizon is extremely hot. Near the black holes, the slowing of time is extreme. From the viewpoint of an observer outside the black hole, time stops. When falling toward the black hole, for example, an object is stretched in the direction of black hole and compressed perpendicular to its fall, in effect, the object can be distorted into a long, thin version of its distorted shape as though being stretched like a spaghetti. Spaghettification is the tidal effect caused by non-uniform strong gravitational field. General relativity says when matter falls in the black hole, information is destroyed, but quantum mechanics says firmly it can't be. Hawking radiation is the black body radiation which is emitted by black holes due to quantum effect near the horizon. Hawking radiation is named after Stephen Hawking, who proposed the idea in 1974. Virtual photons pop out of nowhere because of uncertainty principle. If virtual photons haven't crossed the horizon, they annihilate each other after a short time. But if one photon passes over the event horizon, it gets trapped. The other photon escapes as Hawking radiation. Black holes are not decaying because there is infalling a photon with negative energy, as Stephen Hawking proposed. Black holes are decaying because Hawking radiation is reducing the curvature of space and time. Hawking radiation reduces the mass and rotational energy of the black hole. Since nothing can escape from the gravitational force of the black hole, they were thought to be invincible. However, black holes evaporate by Hawking radiation. The most likely fate of universe is the big freeze. The expansion of universe due to dark energy result in absolute zero temperature. In this case, entropy will be maximum and there will be no energy gradient. The star formation will stop. The existing stars will be out of fuel. Universe will become colder and darker. Black holes will dominate, which will also evaporate by Hawking radiation. The universe that started from hot dense point will end with absolute zero temperature. Another theory about the end of universe is Big Rip. Big Rip is much more drastic than Big Freeze. According to this theory, everything in universe, even space-time, will be torn apart by the expansion of universe until the distance between the particles will become infinite. Dark energy will keep on accelerating the expansion of universe. Space itself will be torn apart. Big freeze is the slow dissipation of matter into entropy, and the big rip is the tearing apart of all matter and the fabric of space-time. Another fate of the universe is the big crunch. It says universe will stop growing, then it will begin to shrink. It will get hotter and denser until it ends in an infinitely dense hot singularity. The fate of universe depends on dark energy. Think of dark energy as anti-gravity, making dark energy and gravity rivals. Dark energy is responsible for expansion of universe. Space is literally being created due to the presence of dark energy. The galaxies are moving away from each other. At present, it is hard to decide if universe will experience big rip, big freeze, or big crunch. The fate of universe depends on the war between gravity and dark energy. Dark energy makes up 68% of the universe. May Allah bless us all. Thank you for watching. Allah Hafiz.